Hey, you've asked for more Roblox reactions? Today we're going to be looking at the realistic pressurized water reactor. This video is by Johnny Lexold, and it is the reactor startup guide and turbine sync. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. Don't claim to know everything there is nuclear, but I can certainly share some knowledge. And this type of reactor, the pressurized water reactor, is the type that I was licensed on. And I must say, I'm liking his uniform. It was before my time, but yes, people in the control room actually had to wear goofy ties. I don't think you ever had to wear hard hats in the control room, but it's pretty funny. Turning off shutdown cooling first. So shutdown cooling, it's your reactor coolant source when the reactor is offline, cooled down, depressurized. So turning that off will help you start heating up. The reason why you have shutdown cooling is decay heat. Fission products still emit heat after the reactor has been shut down. So it's not from the uranium itself, it's from when the uranium is fission, the things that it turns into. Things like cesium-137 or strontium-90 continues to generate heat. So turning that off will get you to heat up. Pressurizer starter heater. That's not a real thing, at least not at the plant that I worked at. You have an array of pressurizer heaters, but this is for gameplay purposes to make your heat up rate go way up so the game would be more interesting. When you're doing a real plant heat up, you're restricted at 50 degrees Fahrenheit per hour. Basically, you're going from 100 degrees Fahrenheit all the way up to 567 degrees Fahrenheit. So not really the most riveting gameplay experience. So I can understand why that's in there. But you would energize heaters, just not a really big one. That would be multiple megawatts of heat. Enable heaters 1 and 2. All right, that's more normal. You see this is in metric, which is cool. Reactor coolant pumps and open inlet and outlet valves. So at the plant that I worked at, the reactor coolant pumps didn't actually have inlet and outlet valves. It was just right in the loop. Smooth sailing, straight line of fluid. But the reactor coolant pumps are another source of heat because they are really big pumps, multiple megawatts. They're big electric pumps, and they're actually going to be supplied from either the grid or from the opposite unit. Most nuclear power plants consist of more than one unit. And those things are big. When you turn those on, you can actually see all of the meters start to move because they have such an effect on the plant's electrical distribution. Auto control. In this game, we're dealing with multiple speed pumps. Again, at the plant I worked at, it was just, they were on or off. Feed water pumps and inlet outlet valves. Okay, now those had inlet and outlet valves, so feed water. Let's back up a moment. There are 2 loops in a pressurized water reactor, like most nuclear power plants. The primary loop, heat is transferred from the reactor vessel through the hot leg, so reactor coolant system piping, to the steam generator, and boiling, unlike a boiling water reactor, occurs in the secondary side, the shell side of this heat exchanger. The tube side right here is the reactor coolant loop. It goes through the cold leg into the reactor coolant pump, and the reactor coolant pump discharges back to the reactor. Very simple, straightforward design. Secondary loop, or the non-nuclear portion, start from the steam generator. Steam flows to the main turbine and then is condensed in the condenser back to a liquid. And here is the feed water pump that moves the condensate liquid back to the steam generator. Now, this is a simplification. In a real pressurized water reactor, you're going to have multiple stages. At the plant that I worked at, it was condensate pump, then you had your feed water booster pumps. Each of these stages increased pressure and increased heat. You also have feed water heaters in these loops where you take steam from the turbine and put it in stages to heat it up further so it can be ready to go into the steam generator. It's just a form of preheating. It's no different than preheating your oven makes cooking a lot more efficient than if you put your chicken in the oven and you had to wait for it to preheat to 400 degrees or whatever. Exact same concept here in a nuclear power plant. Multiple stages of pumps, multiple stages of heaters. And that aspect is not unique to nuclear power. You see these sort of things in any thermal plant, whether it's nuclear, coal, natural gas. One interesting thing, now, it could just be a bit of a weird convention where I worked, but red and green are flipped, as in red being energized, on, open in the case of a valve, its active state, and green being its standby, off, de-energized, or closed. I've heard it was the opposite way in naval ships and possibly in other countries. Just a convention that I'm used to. I'm okay with the game flipping it, as I mentioned in my reaction to Roblox's realistic boiling water reactor video, which if you haven't seen that, I'll pin that down below in the comments. So right here, enable CAR and SJAE. So CAR is a condenser air removal, just a vacuum pump to keep the condenser at a vacuum. Keeping your condenser at a vacuum is crucial to optimizing thermal efficiency, basically producing more megawatts. Now SJAE, same idea, steam jet air ejector, is to maintain vacuum in the condenser. Now, as far as difference, steam jet air ejectors use steam to entrain and remove non-condensable gases by creating a vacuum through high velocity steam, whereas vacuum pumps use mechanical means such as vanes or diaphragms to physically pump the air and gases out. The air ejectors are cheaper, less likely to break down because there's less moving parts involved, but the CAR's vacuum pumps are more precise. So there's your trade-off. Polisher and preheaters. So Polisher is a chemistry control cleanup system, removes chemical contaminants as a means for cleanup and corrosion control. The plant I worked at used a series of demineralizers, below 500 millibars. Yeah, the units I'm used to are in inches of mercury vacuum. You can get it as close to a vacuum as can. A perfect vacuum would be 30 inches of mercury, and the plant I worked at were like right at 29. So you can get these pretty close to a vacuum to make it as efficient as possible. And then they talked about the turbine bypass valve. So you see the main steam line that goes from the steam generator to the turbine. There's another path not shown here where you can go straight from the steam generator to the condenser. And really, it's just about keeping your steam cycle going while the turbine is offline. What the turbine bypass or steam dumps also do is they act as the brakes when you shut down the reactor, because all that steam's got to go somewhere. So just giving us a little bit of steam flow to work with. That makes sense. Video speed 1750%. So it takes a while even in the game. That's interesting. And a lot of startup shifts are really like this. When you're getting the secondary all heated up, a lot of that consists of waiting in the control room, making sure, and even before you do this, all the plant operators have done hundreds and hundreds of different valve lineups, many thousands of component manipulations out in the field that you never even see in the control room. And yet it all depends on the scope of your outage, how much additional maintenance you did in addition to refueling the unit. But that would be the long leg. There's a lot of sitting and waiting in the control room. There you go. Disable main steam isolation. So main steam line isolation is one of the safety systems in a pressurized water reactor. And that's if the event of, say, a steam line breaks or a feed line breaks, you completely isolate the broken line from all of the non-broken lines so it doesn't completely suck the steam or the feed out of all 4 or 2. Not sure if this reactor is 2 loops, but the reactor I worked at was 4 loops, and you don't lose the entire secondary plant. And the big reason is it prevents an excessive cool down of the reactor, the primary plant, in that type of accident. But you need to disable that function in order to start up. And it's perfectly safe because you don't have significant enough steam pressure that it would even do anything to the reactor. Condenser circulation, auto control, that's nice. I was wondering if there were going to be a whole lot of manual controls. But a lot of things work in automatic, which is nice. Video speed increase. Ooh, this thing. Yes, the plant computer, and I could tell they're going for the old school plant computer where it's this old little printout looking thing. It really does log every manipulation you do. If somebody screws something up, you have... Now, it doesn't say, like, the person, because it's not like... It doesn't fingerprint, like, who's turning each switch. Oh, glossary. That's funny. I like it. Don't disable anything from the electrical panel. Did you just remove power to the control room? Oh, and they got Christmas decorations. Okay, in that regard, it was way better than the control room that I worked at, because they had fun Christmas decorations. Here is the plant computers. Demand set to network. I've mentioned this before in other videos like this. You're not really monitoring grid demand in the control room of a nuclear power plant. You're given right-of-way and you are base load, meaning the grid will just let you go up to 100% power, and you will stay there until an outage. So I don't know if that's a game mechanic, but in a real outage, you're basically just going to start up and ramp up to 100% power. And I can see sent to network minus 9.1 megawatts. So that means we're taking 9.1 megawatts from the grid, which makes sense. Turning on reactor coolant pumps, condensate pumps, feed water pumps, and possibly that superheater they installed, but that probably uses magic. 9.1 megawatts is not a surprising number. Line 911. And EDG stands for emergency diesel generator. Rods off, boron off. It's really boric acid that you would inject into the reactor. And boric acid, think liquid control rods. Probably shouldn't jump over control panels in a real reactor. Oh, he's speeding stuff up. Okay, yeah, temperature's going on up. Wow, maybe the cooldown limits are real in the game. And the cooldown and heat up limits. That's kind of funny. All right, so he's at the reactor control area. So looks like he's selecting which control rods to pull. All right, so select the scram rods first and withdraw. So scram is an emergency shutdown, or a reactor trip, as I call it. And you pull those, and you do pull those first, and it is super nice in the game that it looks like he's selecting multiple shutdown banks at once. At the plant that I worked at, you couldn't do that. And you just withdraw those all the way out. There's enough shutdown margin in a reactor that if you pull all of those, you're not going to start up. It's not going to turn critical. And by critical, I mean when the fission reaction becomes self-sustaining, and that amount of neutrons in equals amount of neutrons out. In other words, critical means the reactor is on. So the reactor is not on yet while pulling the shutdown banks, or shutdown control rods, or scram rods, or whatever they just call them. We're speeding up, yes. Just like a real startup, this part is pretty realistic in terms of how slow everything is. Maybe that's how realistic that is. I'm not sure how fun of a game this is if you sit and have to speed up the video that much. Deselect and select the other rods. So these we called the control rods, and they were set to overlap in the right configuration automatically, which is nice. Now you still have to manually withdraw those control rods. Each bank would start stepping and start moving these control rods in a phased sequence in a pre-programmed way, which was nice, so you didn't have to think about it. So you can see here they're selecting individual groups. This little Scrabble board is a map of the core. You didn't have to micromanage that in real life. This pre-programmed way lets you optimize it to ensure that the heat is being produced in an even part of the core. There's two ways you measure that, so that ensures an even radial distribution. You can safely pull the rods, I like that. Now this part here, the amount of briefing you have is with an individual reactor operator, the reactor operator's peer checker, the reactor operator's direct supervisor, reactor operators monitoring the secondary plant and the electrical plant, and additional supervisors, shift supervisors, managers from other departments, a lot of project managers from the outage because this is the very final milestone. It's a point in the real unit that you actually kick people out of the control room because it's a slow process, but it's actually very important and everyone is ready to immediately terminate the startup if something goes wrong, and there's all kinds of criteria they're looking at: reactor temperature, reactor pressure, secondary temperature, levels of water in the steam generators, and a whole list of things that people are monitoring to make sure it's right. There's also reactor engineers, subject matter experts, monitoring all of this. Very, very sacred evolution. The big number you see that's fluctuating right there is reactor period. The reactor period meter is a unit to define how long it takes for the reactor to increase by a factor of E. E being the mathematician's E, that's about 2.7 and some change. So reactor period is a unit of time, typically in seconds. So at this moment, it's going to take 289 seconds for reactor power to increase by a factor of 2.7. The plant I worked at did not use this thing. I've never been a fan of reactor period. Instead, we use something called startup rate. The startup rate is decades per minute, a decade being a factor of 10. So if your startup rate is 1, power is going to go up by a factor of 10 in a minute. If it is 3, power is going to go up by a factor of 1,000 in a minute. And the startup rate limits at the plant that I worked at was 1. We would often start up at around 0.3 to 0.5 decades per minute. Now, in nuclear submarines, it can be 5 decades per minute, or during a fast recovery startup, could be 9 decades per minute as a limit. Yes, 9, as in power level increasing by a factor of 1 billion per minute. Basically kind of an emergency scenario to maneuver. And that's why pressurized water reactors, commercial plants are like freight trains, and submarines are like sports cars. Oh, there's an alarm. We have an off-site grid outage in the middle of a startup. All right, let's see what we lost. At least one grid is down and not the other. Well, they're probably going to need the power if part of the grid got hit by a tornado or something. Is there a way to silence alarms in this game? Should be. Typically when you get an alarm, you hit a silence button, you acknowledge it, so the flashing lights that you see up there will stop flashing, and then you pick up a binder, an alarm response procedure that'll tell you what to do if those alarms are in, but this game might not have that. If it was half, then he might have lost, depending on what it was, that could have terminated the startup. Like if it was, say, a reactor coolant pump under voltage or under frequency will cause a reactor trip, as well as loss of reactor coolant loop flow, reactor trip. And that's because these commercial nuclear power plants are not designed to run on natural circulation. You need to have the reactor coolant pumps. But that's typically what you trip on when you lose reactor power, or you lose offsite power. Do not attempt what I do. He just turned it off, and that is one thing, and you'll see this as different compared to other industries. In some cases, you will do what's called a closed transition, where when doing electrical switching, you'll have something paralleled when switching power sources. Like if you were to swap, say, a bus from source to source 2, you'll close both breakers and have both of them energize the same source, and then you'll open one of them. There's a time limit associated with that. It's typically about 30 seconds, but you will actually see that in nuclear, because in nuclear, you really don't want to lose power to something, compared to an open transition where you de-energize something to transfer from, say, source 1 to source 2. And that's a little different than electrical operations work in other industries. And now he's basically speeding everything up. I guess he was able to get everything back by the use of magic, speeding up a startup. I know several reactor operators that would like to do that in real life. So IPR intermediate intermediate power range or intermediate range. So there are three ranges. Source range is typically measured in counts. So you're monitoring reactor power, quote unquote, even when you're shut down, but it's really just counts to make sure it's still active, because you will have some fissions occur while you're shut down, but it's what's known as subcritical multiplication. It's not enough that it's self-sustaining to the point where the reactor is going to start up. But as you raise reactor power, you're going to get into the intermediate range, which you're talking on the order of microwatts, milliwatts. So the reactor's on in that you're critical. You've pulled control rods enough to make it self-sustaining, but you're not at the point where it's really doing anything in terms of making steam. That's at the point of adding heat, where the heat source from the reactor is significant relative to the reactor coolant pumps and the pressurizer, and that typically occurs around 1% of reactor power is where you start to notice its effects, and at that point is when you would start to monitor the power range, which is typically on a scale of 0 to 100%, and you start looking at it in terms of megawatts. The reactor I worked at was about 3,800 megawatts thermal. Raise IPRs. Wow. And as you raise reactor power, you're going to have to start pulling control rods once you get to the point of adding heat, because temperature will go up. And that's actually a negative feedback mechanism, which is good, because that means power is going to level out and plateau at a certain point naturally. So it's a very controlled react compared to, say, when you're in the intermediate range. There's not really that negative feedback mechanism, so it's going to go up, and it's going to go up continuously until you insert control rods or until you reach the point of adding heat. But as temperature goes up, that's going to lower reactor power. And the reason for this is water is the moderator, and due to thermal expansion, the water molecules become further and further apart. So it's less effective of a moderator. And what a moderator does is it slows down the neutrons produced from fission so they can create more fissions. And less of that is occurring, which lowers reactor power. So you compensate for this by pulling control rods. But I don't think he's there yet in this video. Yeah, you're above 1% power. Here we go. Wait until power builds up a little more. I like that. Disable the pressurizer startup heater. Get rid of the magic thing. Raise temperature set points. Not sure what those temperature set points are for. Those temperature is still pretty low. You do the majority of your heating up before the reactor is online. Now, I didn't quite see what temperature was before he started up the reactor, but you're mostly there. At 0% power, average temperature at the plant I worked at was 567 degrees Fahrenheit, and at 100% power, it's 592. So not a huge difference. Now they're going to start the turbine, all right? Enable the turbine exciter. It's actually for the generator. Now what an exciter does is it generates magnetic fields to induce voltage in the generator. It typically uses a very small portion of the generator's output, converts it into direct current, and generates it and sends it to the generator's rotor to create a magnetic field, because the rotor is the part that spins. And that interacts with the stator, the part that doesn't spin, to create alternating current, which is the generator's main output that eventually goes to your house. So the exciter excites it by generating magnetic field. And now spinning up the turbine to 1500 RPM. I wonder if there's going to be some speeding up here, because that takes a while. There's a whole science behind rolling the turbine. There's periods where you roll and then you wait, and then you roll and you wait some more until you eventually get up to 1500. At the plant I worked at, the number was 1800 RPM. The number was 1800 RPM. But there are certain regions that you want to avoid called the resonance regions. And those are magic numbers, and it entirely depends on the turbine and how it's designed, where when it spins at a certain speed to start to vibrate and eventually lead to mechanical failure. This sort of phenomena was seen in the infamous Tacoma Narrows Bridge accident. Not pretty. Not pretty at all. Like that he keeps going and ignores the alarm, something you'd never do in real life. Ignore if the primary temperature controls are different. Automatic will deal with it. I guess that's one of the things about, I don't know if he has variable speed pumps or what, but it should be fairly straightforward. Everything mixes in fairly easily. That's not an alarm I've ever seen go off in real life. The primary differential temps, and that's where one loop is a radically different temperature than the other three, or the other one, depending on how many loops there are in this plant. It does have silence and acknowledge buttons, just ignoring them. Left temperature high. Okay, that implies that there's just two, if it's left and right, rather than 1, 2, 3, 4. So now we're going up to 20% power. Right around then is where you'd want to sync the generator. Was that shaking coming from the turbine shaking the building? I've never heard the turbine or reactor or really any noise from the control room of outside plant equipment. There's a lot of concrete and steel between the control room and the outside world. Doesn't quite meet the qualifications of a bunker, but for all practical purposes, it might as well be. Not sure what that's simulating in the game, if it's going to be the turbine or the reactor or... Increasing generator voltage when needed, sure. Generator voltage, 6,600 volts. That's low. The one where I worked at, it was 25,000. Which 25,000 is still low relative to the grid. The grid was on the order of 345,000, but it's stepped up. That's from the generator to the main transformers, which step it up that high. Yeah, you're not going to hear plant sounds in the control room, or if you do, it's probably not a good thing. All right, now we're getting ready to sync. Match grid frequency and sync generator. You're actually going to want to go a little more, so that you're going to pick up a teeny tiny bit of the grid. And the reason for that is you really don't want the alternative where you lag the grid. Now this synchroscope is kind of hard to read, so here's a bigger one. This thing's going to be moving, and you're going to want to close the main generator output breaker, which syncs the generator to the grid, when the needle is moving slowly in the fast direction, so clockwise. And there's a bit of a delay. So if you imagine this as a clock, I was always taught to close it at 11:55 with straight up being noon. If you were at 6 o'clock or straight down where you're 180 degrees out of phase with the grid, that's bad. You're going to break your generator. Do not break your generator. Those things are expensive. Well, that looked pretty easy and anticlimactic. Enable second feed water pumps. So you'll see this, you'll turn on additional secondary pumps as you ramp up in power, and you'll do it at various hold points. At the plant we worked at, we had 3 condensate pumps, 3 feed water booster pumps, and 3 steam-driven steam generator feed pumps. We also had a startup feed pump because we didn't have enough, because the turbine-driven feed pumps wouldn't have run because we were just so low in power, but the startup feed pump will get you up to 20% where you're making more than enough steam to run those other pumps. At full power, they'll all be running, with the exception of the startup feed pump. As you raise power at various plateaus, 30%, 50%, 60%, they're going to turn on these pumps and start forward feeding with it, because you're making so much more steam, so you're going to want to have that additional feed flow, and to maintain your steam pressure and feed pressure, differential pressure, in order to ensure a smooth startup and operate smoothly. It's pretty easy, it's just something you need to plan ahead for. I've actually done that specific job as well, being the reactor operator that ran the secondary, and just like anything else, just plan ahead. And there you have it. They'll continue to go up and just ramp up to 100%, where they'll just be turning on more and more things. So congrats, you've now started the reactor. Now try to meet the demands. Again, you wouldn't do that. You're base load. You're not load following in real life. but unless something went horribly, horribly wrong with the rest of the grid. But if it's only 70 megawatts on the grid at around 20% power, well, that would imply that this reactor is only 350 megawatts. It might be higher than that because he still had the turbine bypass valves open. I'm not sure how open they were, but this could be like, say, a 400 or a 500 megawatt unit, depending on how much steam he was sending to not the turbine. Because after all, megawatts only count if you're sending your steam to the turbine. But that kind of makes sense for this reactor to be much smaller if it's just a two-looper. But overall, I actually thought this was fairly realistic, including the watching paint dry portions of it where you wait for things to heat up. So I thought they did a really good job with this mod, other than a few little idiosyncrasies here. But these modders are getting pretty good. I can tell they either worked in the industry personally or know a few guys that did. Thank you very much for watching. I'll see you next time.